Okay, now I was mentioning before what these devices do, like what are the differences between the routers and the switches, and where they fit into the layer numbers, like the layer 1 versus layer 2 versus layer 3. What this is referring to is what's known as the OSI model, or the Open Systems Interconnect model. Now, the idea behind this is that it was a standards-based organization. It's called the International Organization for Standardization, that they wanted to come up with a model that if I wanted to make an Ethernet switch, that I could follow the standard that Ethernet defines, and if I plug it into someone else's Ethernet switch, it's automatically going to work. Because as long as we follow the same conventions of what Ethernet does, and I constrain myself to that layer that Ethernet sits, I should be able to connect it to other vendors, and it's going to work. Now, originally when this network equipment was first starting to come out, like IBM's implementation of networking with the CCNA protocol, which for the vast majority of cases it's pretty much long gone, but originally CCNA was a proprietary protocol that IBM wrote, so you couldn't just make a switch that ran CCNA or you make a router that ran CCNA, because the details of how it actually worked, they didn't publish it. So the idea behind OSI is that a lot of this stuff in networking is going to be standards-based, that the standards bodies get together and they decide this is how we're going to do this particular protocol or this particular design. Then if you want to make a device that does this, just follow our standard and eventually it's going to work. Now, a lot of these are defined by what is known as the request for comments, or the RFCs. And the RFCs are part of the Internet Engineering Task Force, or the IETF, where basically IETF is a bunch of network engineers that get together and say, this is the problem we're trying to solve. We're going to define how we're going to solve it. Then if you want to implement this, you can follow our directions. So we don't tell you how you're actually going to program your devices, like in software, or how your hardware should work. Just the final result of it should do A, B, and C in order to get to D.
For the exam, have they gone away with, or done away with IPX, SPX, or AppleTalk?
Pretty much, they're not going to be covered anymore. So mainly we're focusing just on IP version 4 and IP version 6, where originally that was another limitation, that the IPX and the SPX protocols were invented by Novell as part of the NetWare suite. So the problem is you couldn't really just write a router that ran IPX, because it was proprietary to how they developed it. Where in the case of the ones that we're dealing with now, pretty much all networking vendors followed standards practices, because most of the time they know someone's not going to build a network with every single device as being Cisco, or every single device as being Juniper. So if I have a Cisco router on one side and Juniper on the other, I want to make sure that they can talk to each other. Especially when you look at like certain government requirements, that they'll say you can't use proprietary systems, that you have to design the network in some fashion, that if I want to take my money and move it from Cisco to somebody else later, then the network is still going to work, that I basically am not relying on just them in order to do this. So the key here of these RFCs, the vast majority of the protocols that we're going to talk about, like Ethernet, like IPv4, the IP routing protocols like RIP, OSPF, these are defined in these requests for comments. And if you wanted to get the real behind-the-scenes details of them, you could reference these. A lot of the times they're very hard to read, though, because it's very nitty-gritty technical details. But the overall point is that this is part of what the OSI model is used for, that we can build these different standards, and then the final result of it is that the equipment is automatically going to work with one vendor talking to another one. Now, the model itself is broken up into seven different numbered layers, where it goes from the top down. It starts at the application layer to presentation, session, transport, network, data link, and physical. Now, we can then further subdivide these into the upper layers and the lower layers, where the upper layers of the model are mainly dealing with the application. So this would be, for example, when I open up a web page and I type in the URL, my web browser is going to ask the network, I'm trying to get to this site. So the upper layers, which are the upper three, the application, presentation, and session. Mainly these are dealing with talking to the application. So how do I get the data from the web browser and then format it into a way that I can send it over the network? Then when it comes out on the other side, how can they reformat it so it appears as a web page or it appears as an image or a video on their side? Where the lower layers, which are 4, 3, 2, and 1, the transport, network, data link, and physical, this mainly deals with how the data is actually transmitted through the network. And for the vast majority of network engineering, this is where we're going to focus on, layers 1 through 4. Where stuff like 5, 6, and 7, this would be if you were a programmer who's writing an application that talks to the network. So anything that's related to the routers and switches, this is going to be anything that's between layers 1 through 4. Where specifically the definitions, the application layer, this is the one that talks to the end host. So it's not going to be your actual application itself. Like let's say you're trying to check your mail. You're going to have an application that's your email client. But this is then going to talk to the application layer saying, I'm trying to send a mail message to someone, or I'm trying to retrieve the message from them. Or if I want to transfer a file from one computer to another, I have the actual application that then asks the network, can you send them this file and make sure it got there? So this is where we would have things like the actual email protocols, the file transfer protocol, and then one that we're going to spend a lot of time on this week, which is Telnet. This is one way that we can get into the network devices to actually make changes on them. So if I want to configure my Cisco router remotely or the switch remotely without having to be physically connected to it, the Telnet protocol is going to allow me to send commands to it and then get feedback from the command line. The sixth one, the presentation layer, mainly this deals with the actual encoding of data. And this is where you would find things like how is a JPEG working differently than a PNG file? Or how does ASCII encoding work differently than different character sets? So you would have your web browser, for example, say, I want to send this image to them, but I don't want to know all of the details of how you actually turn it into the data that goes over the network. So I'm going to send it to some sort of presentation processing that says, take this image and then turn it into a JPEG to actually send it across. Or I want this text, I want it encoded as ASCII, so on the other side they actually know what the end result of it is. Then the fifth one, the session layer, this is generally how the end hosts figure out who they're talking to, or to manage multiple sessions at the same time. And the best way to think about this is that for a web server, a lot of times it's going to have connections to multiple clients at the same time. So it's going to need to figure out, when I have a web request coming in, which user is it actually from and what piece of data am I supposed to deliver onto them. So the key being that these upper layers, 7, 6, and 5, these are mainly dealing with the application. The lower ones, starting at 4 and below, this is what we're going to be focusing on. So number 4, which is the transport layer, the main goal of this is that we're going to take the data from the upper layers, like the session, presentation, and the application layer, and then I'm going to break it up into smaller parts in order to actually send it over the network, which is known as data segmentation. Now, this is also used for establishing end-to-end connectivity, and we'll see that there's 2 key network protocols that work at this layer that we're going to be spending a lot of time with, which are the transmission control protocol and the user data protocol, or TCP and UDP. Probably 99% of your applications are going to be using one of these 2 protocols to talk to each other. Where like web browsing or FTP file transfers, those are going to use TCP for communication. Where your IP phone calls or maybe your video traffic, that's going to be running over UDP. So depending on what the application wants to do at the upper layers, it's going to ask the network, I want to get this to the other end, but I want to make sure it actually got there. And this is one of the main things that the transport layer does, that it can make sure that not only did I format the data correctly, did it get there, but ask them to tell me, did you actually receive it? So is what we call the transport of the network, is the transport actually reliable? Then if something goes wrong, if for some reason the packet didn't get there, I want to be able to fix that problem, basically do error recovery, or what's known as retransmission, so that the web server doesn't have to keep sending the same reply to the client. The third one, we have the network layer. This is what mainly is going to be doing the path selection and then the connectivity between the end host, which is going to be the routing functions. So this is mainly where our layer 3 IP routers are going to work. This is also where we have the, actually that should say logical addressing. The logical addressing, this is going to be the IP version 4 and the IP version 6 addresses. Like if you were to go to your Windows machine and run the command ipconfig, this is what you're asking it. So what is the layer 3 logical addressing of the device? Where in this case, it says it's running IPv6 addresses and IPv4 addresses, which is going to be defined at layer 3. So when we send our traffic out to the internet, the routers in the middle between us as the sender and then someone else as the receiver, they're the ones that's looking at this field, the IP address or the IP version 6 address, and then figuring out how do I actually send the traffic. So typically this is where the routers are going to sit, and then also anything that's directly related to IP version 4 addressing or IP version 6 addressing. These are considered layer 3 protocols. Whereas compared to the previous ones, the TCP and UDP, those are considered layer 4 protocols because they have to do with the end-to-end connectivity, mainly the reliability of the delivery between the end hosts. So we'll see when we actually look at the end result of this and look at like a conversation of a web session between the client and the server. There's different pieces of the data that get encoded at layer 4 versus at layer 3, which is going to be the IP addressing. Then the next one underneath that, the data link layer, this is what's actually going to deal with doing the final formatting of the data to actually send it over the physical links. So this is where we're going to have Ethernet or our WAN protocols like frame relay or PPP. So the Ethernet switches have physical cables that are plugged into them, and when my web browsing session gets to the layer 2 switch or the Ethernet switch, it's the one that actually needs to take this and turn it into an electrical signal or turn it into an optical signal. So it needs to do the final formatting of the data before it actually goes on to the wire or the physical media. So this needs to actually control access to that media. We'll talk about when we get into more specifics of Ethernet, what's known as the carrier sense multiple access with collision detection, or CSMACD, basically what controls who can send data when. Because the physical cables that are connecting the network together, we may have multiple devices that are sharing those at the same time. So the layer 2 protocols, they need to figure out when do I actually send my web browsing session versus my phone call. They're the one that's controlling the actual physical access to the media. So this also means then we need some way for the devices to talk to each other directly at this layer, at layer 2. This is where the physical addressing comes in. So when we compare a layer 3 protocol like IP to a layer 2 protocol like Ethernet, Ethernet uses a physical or a hardware address to communicate, where IP uses a logical address that we can manually change in order for the devices to communicate. So we'll see when we actually look at the data flows. We need to know what devices are going to be processing the info at layer 2 versus layer 3 or higher. And that's ultimately going to control what do they do with the data once they receive it. Now typically you'd also have error detection here, which a lot of the times is done with a CRC check, which is a cyclical redundancy check. Basically it's another error checking to make sure that when I put the frame onto my copper cable and it gets to the other side, was there some sort of interference that caused it to have an error? So again, typically this is going to be where our Ethernet switches would be. So the devices would be like our switches. Also, wireless access points are generally going to work at layer 2. And then the protocols are going to be like Ethernet, frame relay, and PPP. So the LAN and WAN protocols, those work at layer 2. Then lastly, we have the physical layer. This is going to be the actual physical properties of the media. So when I'm connecting two switches together, do they connect over copper or do they connect over fiber? So this would be like your electrical functions of the link, or the physical data rates. When I look at Ethernet that runs at 100 megabits per second for fast Ethernet versus gigabit Ethernet at 1 gigabit per second, that's going to be a physical electrical function of the link, of how often I actually send the pulses on the interface. Okay, this is where you would also define the physical connectors. So when I have the fiber cable plugged into the router, what is the actual connector that I physically plug in? And there's different types of standards that are going to define this. This would also be how far can you send the traffic over the cable. So if I need to send my data from New York all the way to Los Angeles over one physical link, then the layer 1 properties are going to come into play. So if it's an electrical signal over a copper interface, typically that's not going to work because the signal can't go that far. So this would be different physical functions of the actual cable, like the optics, or like the optical wavelengths. And in the case of wireless, this is going to be your frequency. Like when we talk about the difference between 802.11b or 802.11g and n, they run at different wireless frequencies in order to send and receive the data. But in this case, that would be considered a physical function. Where in the case of Ethernet, your physical media might be your copper cable, but in the case of wireless, your physical media is the air. It's the radio frequencies exchanging between them. So again, this is where our cables are going to be. And then some physical layer 1 devices we'll talk about later. For Ethernet are repeaters and hubs, where basically these are obsolete devices. Now, I wouldn't be surprised if on the CCNA exam or like the CCNP exam, they ask you specifics about the different layers. So this is typically one of those things you can't get away with not memorizing what the naming is and what the layers do. So there's a couple common mnemonic devices for this. Or if you go from top down, it's all people seem to need data processing. Or if you were to go the other way from 1 to 7, please do not throw sausage pizza away. So physical, data link, network, transport, session, presentation, and application. And those should be covered in these Cisco Press books as well. These two are pretty common for it. So I will make some printouts of this as well, but it's one of those things that you want to make sure you know the names of them and then specifically what are the functions of them. Okay, so why do we want to use this in the first place? One of the key reasons is that when we look at a device in the network, like a layer 2 Ethernet switch or a layer 3 IP router, is that when we segment the operations into these different layers, the layer 2 switch really only needs to be aware of what the layer 2 protocols that are running are. So it doesn't need to know about IP addressing, or it doesn't need to know about web servers or HTML. So a web server, likewise, it doesn't care if I reached it using an Ethernet link or a wireless link, because the web server is running at layer 7 as part of the application. It doesn't care how I used at layer 1 or 2 in order to get there. So likewise, the Ethernet switch, it doesn't care if it's sending IP version 4 packets or IP version 6 packets, because that's not its job. Its job is at layer 2, not at layer 3, at the network layer. But also, like I mentioned, it's going to allow us to have interoperability between the vendors. So if I have a Cisco Ethernet switch and it's talking to a Netgear switch, there's not going to be any problem with that, because they're both agreeing on what the standard that Ethernet is defined as at layer 2. The same thing is going to be with routers. I could have a Cisco router on one side, Juniper on the other, as long as they agree on the standards for IP and IP routing at layer 3, then they're going to be able to talk to each other. Same would be true of like your applications. So if I talk to a web server that's running on Linux, it doesn't care that I'm coming from my Windows machine or coming from Mac OS, because they're agreeing to run the HTML standard that's defined at layer 7, at the application layer. Now, as we're actually moving the traffic between the endpoints, like from our web client to our web server and back, we go through what's known as the encapsulation and the decapsulation process. And this is essentially when two adjacent layers of the OSI model start to talk to each other. Like when layer 1 asks layer 2 to send the traffic upstairs, or when TCP at layer 4 says to the layer below it, which would be IP, I'm trying to get the traffic to this particular destination. So encapsulation and decapsulation is what we use to build what's known as the protocol data unit, or the PDU. And the PDU is what describes what does the data look like when we're dealing with it at layer 2, or what does the data look like when we're dealing with it at layer 3 or layer 4. Where the encapsulation process, this happens on the way from the sender to the receiver, where we're going to start all the way at the application layer, and we're going to add levels of formatting to finally we get down towards layer 1, which is the physical media access, and then we could send the data over the link. Whether it's a copper interface or whether it's wireless, the upper layers, they're not really concerned with that, because they only need to ask the layer above them or below them exactly what's going on. Where on the other side, it's going to be the opposite, the decapsulation. This is where we are removing the formatting from the lower layers, and then we're passing it up. So when an Ethernet switch receives the physical bits from the wire, it's going to take that framing off. It's going to look at the layer 2 information, like the Ethernet MAC address, and figure out what to do with it. Then once the packet actually gets to the end host, it's going to look at the layer 3 information to say, is this my IP address that the packet is destined for? Then at layer 4, it's going to look at what's the transport protocol. Is this a TCP session or is this a UDP session? From there, then it can continue to pass it upstairs, saying, okay, to the presentation layer, now this is a JPEG. So tell the application, your web browser, to actually make it appear like it's a picture. Now these PDUs, when we look at the lower layers, which remember are layer 4 through layer 1, there's specific names that they give. What does the data look like at layer 4 versus layer 3, 2, and 1? And the first of which in the transport layer is the segments. So in the case of a TCP or UDP segment, that means that piece of data is working at layer 4. Where at layer 3, the internet layer, this is going to be the packets, or the network layer or internet layer. Then at layer 2, the data link, this is a frame. So in the case of Ethernet, you're talking about Ethernet frames or frame relay frames or PPP frames. Then finally at layer 1, this is where your actual physical bits are. Like they would be electrical signals, or they would be optical wavelengths, like frequencies of light that are going over the fiber optic cables. Now again, the encapsulation process. This is what's going to happen when the traffic is moving from the top down. So when we start at layer 7 and we start to move towards layer 1. Now each way along the path, as we move from 7 to 6, 6 to 5, and so on, each of the layers is going to add its own formatting, which is part of the encapsulation process. And this comes in one of two ways. The first of which is called the header, or the encapsulation header. Basically means new data that we're adding onto the front of the packet, or to the encapsulation trailer, or something that's going on behind the data. So the idea is that as the packets move down and down and down, they're going to get new encapsulations on until they finally reach either the next layer, and it continues, or until it reaches layer 1, and then it's finally going to be sent over the link. So if we were to try to visualize this, And let's say that we have a web client that's over here that is trying to talk to our web server. Now, in the middle, we really don't care about what are the details of how these devices are connecting. So again, typically in a network diagram, this is where you would see the network cloud, because I don't really care how I get from point A to point B, as long as I can. So on the web client, they're going to talk to the application layer and say through their web browser, I want to start a session to them. Like this is going to be something like our HTTP GET that says to the server, I want to download this particular file. So then as it goes down through presentation and session, again, these ones here are the upper layers. As we get down towards the lower layers, this is mainly what we care about with the encapsulation and the decapsulation process. So at the top, we're going to start with our actual web request. So the web packet is coming from the client. It gets down to the transport layer, and the transport layer is going to add its own header onto this. And in the case of a web communication, this would be a TCP header. Then TCP says I need to send it to the next lower layer, I need to send it to network. Network is going to add the IP header. So we take the original data that came from layer 4, gets down to 3, we're adding the IP addressing information, the layer 3 header. Then as it gets to layer 2, depending on what the media is, let's say we're going over an Ethernet switch, it would mean that we would have to take this full IP packet and add an Ethernet header and then an Ethernet trailer. Okay, we'll talk about later specifically what's inside the Ethernet frame, what's inside the IP packet, what's inside the TCP segment. Then finally, when we get down to the physical layer, this is going to be the actual sending of the data. So this is going to be like the actual binary communication. But the idea is that once the data gets to the other side, the physical layer on the receiver is only really concerned with what happened on the physical side of the sender. So it receives these bits, and it says, I need to send it up to the next layer, which in this case, my data link layer, let's assume we're running Ethernet. So it's going to take the physical framing off, and it's going to show the end result of the Ethernet frame. So inside of Ethernet, we still have our IP packet, we have our TCP segment, and then we have the actual web application. Layer 2 is then going to remove its own data encapsulation. It's going to send it up to the next layer, to network. So now the network layer gets it and it sees just an IP packet. Then likewise, the network layer is going to send it up to transport, but it's going to remove the network layer information. Then the network layer continues to send it up. Finally, the server gets it and sees that it was just a web packet. Now, the overall idea with this is that since the client and the server didn't need to deal with all the details of the lower layers, they don't really care if they're directly connected over a physical cable or if they're going over the internet to reach each other, or they're going over like a VPN connection to reach each other. As long as layer 1 on one side can talk to layer 1 on the other side, that's all that the protocols care about. The same with layer 2 to layer 2. As long as these guys agree on the Ethernet standard, they're going to be able to read each other's data. Same with layer 3. If I'm running IP version 4 routing or I'm running IP version 6 routing, the transport layer doesn't care, because the only thing they're concerned about is their own header information, the TCP information, and likewise up and up and up. So on the sending side, this is when we're doing the encapsulation, where we're adding that additional data. On the receiving side, this is where we're taking it off. We're doing the decapsulation. So again, that's going to be the reverse. So we're starting at layer 1. We're moving up the stack. So we're going from 1 to 7. Each layer is going to remove its own information, Like at layer 2, it's going to take the Ethernet header off, pass it up to IP. Then when IP gets it, it's going to continue to pass it up and up and up until it finally reaches the application layer.
Auto negotiation in your laptop, that physical.
That would be part of layer 1 and 2. Yeah. Sometimes you'll see the functions overlap between them, but as a general rule, most of the time you can categorize like a layer 4 versus a layer 2 function, and that allows the vendor to focus just on that. So, like let's say your actual network card, they don't care if you're running IP on top of that. They only deal with Ethernet and then your physical connection, which would be the cabling, and they deal with just that layer 1, layer 2 interaction, and then the rest of it is going to be somebody else's job or some other piece of software's job. Now there's a second model that basically talks about the same thing that's known as the TCP/IP model, which is for transmission control protocol and the internet protocol. And this is mainly what we're going to be dealing with. Now there are other protocols that you can use on networks like IPX, as I mentioned, for the Novell NetWare stuff, but pretty much every protocol up to this point has been made obsolete by IP. So 99% of the stuff in the network is already going to be IP. Where this OSI model, it originally wasn't directly designed for TCP and it wasn't directly designed for IP. They came up with their own model that was similar to this, but it's simplified into just 4 layers. Where instead of the full 7 of OSI, we have just 4 that are application, transport, internet, and network access. And these 4 together, they make up what's known as the TCP/IP stack, or basically the IP stack. Now, in the case of the TCP model, for the application level, this is the same as the layers 5 to 7 on the OSI side. So it eventually does the same thing, which is to talk to the application, but we're really not making the distinction between when you're talking to the web server and then when you're formatting your ASCII data, and then when you're keeping track of the sessions. So from TCP's point of view, this is basically their API to talk to the applications. So if I write a web application, I don't need to deal with the specifics of what TCP is doing. I just need to say send the data or receive the data. And then behind the scenes at layer, the transport layer and below, they're the ones that are dealing with those specifics, the actual transport of the traffic. So this is where the transport layer is. It's the equivalent of the transport layer on the other side of layer 4. So this is where we're providing the network services to the application, and this is where both TCP and where UDP sit. Now the differences between them are that TCP is what's known as a connection-oriented protocol, or it essentially has reliable communication. That if I send you a message, you have to tell me that you got it before I continue to send you more data. So then if you don't tell me that you got it, or what's known as an acknowledgement, I know that something wrong happened, and then I can do retransmission, or basically send you the packet again to make sure you do get it. Or in the case of UDP, this is known as a connectionless communication, or an unreliable communication. So we'll see when we look at different types of network applications, there could be a reason where you would want to use one versus the other. Where let's say, like in the case of a database replication, most likely I would want to send that over TCP so that when I send whatever my database entries are to the remote server, I want to make sure they actually got it. And they're going to have to tell me that they got it before I continue to send more data. But on the flip side, let's say like an IP phone call or a video that you're watching over the internet. If part of that data drops, I don't want you to send it again, because it doesn't make sense that if the first portion of my sentence you can't hear it, that the network tells me again a couple seconds later. So for certain applications, if data is lost, you just forget about it. It's not going to make a difference. Where the next one, the internet layer, this is going to be the equivalent of the third layer of OSI, which is the network layer. This is where the Internet Protocol is going to sit, either Internet Protocol version 4 or Internet Protocol version 6, IPv4 or IPv6, respectively. where the main thing that this is going to do is going to give us addressing, the IP addresses or the IPv6 addresses. It's going to be where routing happens, so where the layer 3 IP routers work, and when we do what's known as fragmentation or reassembly, which I can take larger pieces of data and then break them up into smaller packets in order to send over the network. Then the last one, the network access, this is the equivalent of layers 1 and 2 in OSI. So if you were to look at these side by side, they essentially accomplish the same thing. It's just different terminology that's in one versus the other. Where for the TCP model, the application layer is combining all of the upper layers of OSI. Then transport is equal to transport. Network and internet, this is both where IP sits. And then the network access, this is anything that's related to the layer 2 functions like Ethernet, or the physical functions like sending the traffic over copper or sending the traffic over an optical network.